Have you ever looked into a mirror and noticed that no matter where you stand, the light from your face finds its way back to your eyes? That's because light has an amazing property. It can trace its path exactly in reverse. This is known as the principle of reversibility of light. It says, if a ray of light travels from medium 1 to medium 2, it can travel back from medium 2 to medium 1 along exactly the same path, provided the conditions are identical. This works for air, glass, water, or any transparent medium, and it's not just a neat curiosity, it's the very reason many optical devices work reliably. Now let's express this principle mathematically. For the forward path from medium 1 to medium 2, we write nu1 to equals sin I divided by sin r, where I is the angle of incidence and r is the angle of refraction. For the reverse path from medium to back to medium 1, we write nu to 1 equals sin r divided by sin I. When we multiply these two, nu1 to times mu to 1, the result is always 1. This means the refractive indices in opposite directions are reciprocals of each other. Example, if the refractive index of glass with respect to air is 1.5, then the refractive index of air with respect to glass is 1 divided by 1.5, which is 0.667. Reversibility also affects how we think about wavelength changes. When light travels from a rarer medium to a denser one, the refractive index is greater than 1, so the wavelength decreases. We write lambda prime is less than lambda. When light goes from a denser to a rarer medium, the refractive index is less than 1, so the wavelength increases. Lambda prime is greater than lambda. But here's something important, the frequency never changes. Only the wavelength and speed change when light crosses into a different medium. In air, we say c equals f times lambda. In the medium, v equals f times lambda prime. So why is this principle of reversibility so important in practice? It's used in optical instruments like periscopes, telescopes, and camera lenses, ensuring the same image quality whether light enters from one side or the other. Retroreflectors use it to send light back exactly along its incoming path. Think of road signs glowing brightly in headlights. In laboratories, it helps align optical paths perfectly during experiments. Even fiber optic cables rely on this principle to guide light back and forth efficiently. Let's solve a quick problem. We are told that the refractive index of air with respect to glass is 0.67. We need the refractive index of glass with respect to air. Step 1. Write the relationship nu1 to times mu to 1 equals 1. Step 2. Substitute 0.67 times mu to 1 equals 1. Step 3. Rearrange nu to 1 equals 1 divided by 0.67. Step 4. Calculate, that's approximately 1.49. So, the refractive index of glass with respect to air is about 1.49. Let's quickly revise. The principle of reversibility tells us that light can retrace its exact path if conditions are unchanged. Forward and reverse refractive indices are reciprocals of each other. While frequency stays constant, wavelength and speed change depending on the medium. And in real life, this principle is behind the accuracy of lenses, mirrors, fiber optics, and many optical devices. I hope you now see how this seemingly simple property of light underpins much of optical science. See you in the next session, where we'll explore another fascinating concept of physics. Asterisk.